The main event for today is with respect to assignment 1. It's basically a walk through what we're going to be doing for assignment 1. But at the same time, it's kind of a more in-depth overview of the mechanics of learning neural network models, which is also really important because we use them for most things that we do in NLP nowadays. So by doing this kind of in-depth, you will understand the models you're using well and be able to make well-motivated improvements to them. Basically, when training neural network models for NLP or anything else, nowadays it is very convenient to use toolkits that are implemented to do this sort of thing. So this is kind of in chronological order from the top. Theano, I don't think many people in this class, if you've started recently, will have used Theano, but it was kind of one of the seminal things at the beginning of deep learning. And then we go all the way up to things like JAX, which are relatively new neural network toolkits. And so then what we're going to do is we're going to create the newest neural network toolkit that, of course, everybody's going to be using in a couple of years. No, just kidding. Yeah, so basically, Min is a neural network toolkit implemented for this class by me and Jisung, who's the wonderful TA who will be helping you out with this assignment if you have questions, along with everyone else. So in order to demonstrate what a neural net, oh, sorry, and let me go back one more time. So you won't be using Min to do any of your neural network research. In fact, starting in the second assignment, we're going to be using PyTorch. But one problem with using PyTorch or TensorFlow out of the box is they do so many things for you that it's sometimes hard to understand what is actually happening. Like, for example, do you know how your parameters are initialized in your neural network model? How are they randomly initialized at the beginning of training or something like this? Or do you know why your model is giving you for example, why your model is giving you an NaN in the middle of training? Why are you getting a not a number in the middle of training? And that kind of stuff, because so many things are abstracted away, sometimes it's hard to see on your own. So that's the motivation for building one of your own and understanding the internals deeply. As an example app, I'm not going to do language modeling because language modeling is a little bit slow to train. Instead, we're going to do something like the bag of words classifier, but it's going to be a little bit more complicated than the bag of words classifier. And specifically what it is it's a deep contextualized bag of words model deep continuous bag of words model. And what this means is we have some word embeddings. These will be trained together with the model, although you can also import word embeddings from somewhere else if you want. And you add these word embeddings together and get a vector. And then you run this through a couple layers of nonlinearities to kind of combine the different features in the vectors. And then you multiply this by a weight matrix, add a bias, and get some scores for doing classification. And in the assignment, we're going to do classification on sentiment analysis. It's our typical stereotypical example. But this could be used for any sort of text classification, of course. And an algorithm sketch for a neural network application code looks a little bit like this. First, we create a model. And when I say create a model, I mean we define the shape of the computation that we want to, or the shape of the parameters, basically, that will go into the model. And then for each example, we create a graph that represents the computation that you want to do. Calculate the result of that computation. And if you're training, you perform backpropagation, update parameters, and then you're done. This in particular is a sketch of a dynamic neural network toolkit, which contrasts with a static neural network toolkit based on static computation. PyTorch, so some of the examples back here that I gave, PyTorch, Chainer, and Dynet are completely based on a dynamic computation. Things like Theano and Caffe were entirely based on static computation. TensorFlow started out being static, and now with TensorFlow Eager supports dynamic computation. JAX is mostly static, I guess. And the difference between these is basically whether you define the computation that you do every training example. And there's advantages and disadvantages of doing this. The advantage of doing this is it gives you more flexibility. And for example, you could build a robot that walks around the room and listens to utterances of the person in the room. And every time it gets a new utterance, it will try to do a different thing. So like you say, go pick me up an apple, it will run over to the refrigerator, activate its like refrigerator door opening network, and then open the refrigerator door, and then like look for apples. It will activate its like separate computation for looking for apples in the refrigerator or something like this. And in order to do something like this, you would need basically a dynamic way to do computation, because you'd be doing different computation for like based on the results of what you computed before. Dynamic neural networks are very well suited for something like this. They're also well suited for a thing like maybe you have a sentence, and the sentence is parsed into a parse tree, like a syntactic tree that we're going to be talking about before. And in order to parse that syntactic tree, one sentence might have a tree that looks like this. Sorry, I should use the dark marker. One sentence will have a tree that looks like this. Another sentence will have a tree that looks like this. And because of this, the computation that you would need to run would look different every time. So dynamic neural networks are particularly well suited for that kind of thing. The problem with dynamic neural networks is, or dynamic neural network toolkits, is that because you need to redefine the computation every time, that's a bit slower. It's also harder to like deploy, you know, a computation graph directly to like production or something like this without deploying all of the app code in Python or whatever like that with it. So PyTorch, for example, has ways where you can write an app in PyTorch and then export it to something like Caffe2, which is a static toolkit. Yes. I got a question on Zoom, which is this the same as the difference between eager and lazy evaluation? It's actually not the same thing as eager and lazy evaluation. The difference between eager and lazy evaluation is that whether you define the computation first and then calculate the result later, that's lazy evaluation, or if you define the result and calculate the result at the same time. So basically, you can have this. You can have static and lazy, dynamic and lazy, dynamic and eager. And the top one is things like TensorFlow 1.0, TensorFlow 1.0, Caffe2. The ones at the bottom are things like PyTorch and TensorFlow Eager. And there aren't that many in the middle. The one in the middle is Dynet. But yeah, basically, you can have all of these combinations up here. Okay, maybe I'll go into the details of each of these steps so these become more concrete, and we can go back to that if we want to go back to it later. Okay, so I talked a little bit about tensors last time. I'm going to talk about them in a bit more detail now. And in any neural network toolkit that we want to use, we will have a numerical computational backend. And if you remember, neural networks are basically things that make big computations out of a bunch of small computations. And the numerical computation backend is the thing that will execute these like elementary computations for us. So for example, PyTorch and TensorFlow use things like MKL, cuDNN, custom written kernels. The reason why is because these things execute very quickly. They are very efficient and can blow through really large operations. For Min, we are going to use NumPy, which I think a lot of people are familiar with, or alternatively CuPy, which is a version of NumPy that runs on GPUs. This might be kind of interesting for you if you like do lots of things on NumPy and are tired of it taking a long time for really long computations. So CuPy allows you to do things on GPU. So NumPy, I think a lot of people are probably very familiar with it, but basically it allows you to define matrices like this and take the matrix multiplication between them and calculate the results, et cetera, et cetera. It has many, many different operations, so it's particularly well suited for implementing, the back end of the neural network toolkit. Okay, and tensors are basically n-dimensional arrays. They have multiple dimensions, anywhere from a scalar that has only one element to a vector which has 1 dimension worth of elements. So that would be a length 4 vector, a 4x4 matrix, or a 4x4x4 3-dimensional tensor. A tensor is any of the above. A tensor can have anywhere between, I guess you could call a scalar a tensor of 0 dimensions. So 0 dimensions to, however many you want. These are widely used in neural networks just because, many of the operations we want to do like this. One thing that we note is in Min, in the neural network toolkit, and in a lot of other neural network toolkits, for each of these tensors, we say both the values that are calculated and the gradients of the with respect to the values. So basically, it saves both the value itself and the derivative of the final value in the matrix in the final value of the neural network with respect to this. And the reason why, of course, is because this is necessary for backpropagation. Okay. So tensors in neural networks can represent basically anything that we have in a neural network. They can represent things like parameters, such as the word embeddings that we're going to be using. They can represent the weight matrices that we're going to be multiplying or adding together, or the weight matrices here. They can also represent our intermediate values. So they can represent, the sum of all of the word embeddings or the result of a hidden layer computation, other things like this. So our tensor data structure looks a bit like this, and it consists of the data. So the data is is, you know, the actual forward computed data. A gradient, where the gradient should be the same size as the data. One interesting thing within the Min code that you will notice is Min supports some degree of sparse computation. And the reason why it supports sparse computation is particularly for example, word embedding matrices, where it's very common to only update like one element of the word embedding matrix at a time. And this is an important thing for efficiency. And we added this to the Min toolkit because this is something that's very widely used in like neural networks for NLP, but would be a good thing for you to know about. Another thing is which operation was this tensor generated from? So this is useful for like backtracing and you know, running algorithms. Any questions so far? Pretty straightforward. Okay, great. So the next thing is model and parameter definition. So this is, oh yeah, sorry, 2 questions.
Elaborate a little more on how the sparse computation makes it faster.
Yeah, sure. I believe I have that later. If I don't get back to it, I'll get back to it then. Yeah.
What's the XP library? Is not seeing the XP library.
It's an alias number.
Yeah. It's an. So the question was, what is XP? It's an alias for either NumPy or CuPy. It's your. So I guess x is a variable. So x is equal to n or c. Yeah, but that's another interesting thing about how this was written, which is basically this allows you to switch your numerical computation backend, which is also a feature that neural network toolkits often do. So that, you know, they often allow you to calculate on CPU or GPU, and that's how we realize it here. Cool. Another thing is model and parameter definition. So that's our first step here. And the way we can create a model in app code, so this is not in the backend, this will be, oh, one thing I should mention is in the assignment, there's basically 2 files that you're going to implement. One is classifier.py, and this is your application code. And then another one is minn.py. And this is your backend code. So normally when you're implementing a neural network for NLP, you never would touch the backend. You just use the backend as is. That would be your import torch or import TensorFlow. And you would only be writing this classifier part. This time, the classifier part is already written for you, and you need to write the backend, basically. So this is how we would implement the app code. So basically, we set our embedding size, our hidden layer. We add some parameters. So this is our word embedding parameters. We have the number of words by the embedding size. And then based on the number of hidden layers that we have we implement basically a matrix where if it's the first layer, we input the size of the embedding and generate something of the hidden size. If it's a later layer, we input something of the hidden size and output something of the hidden size. So just to demonstrate this kind of like intuitively, you can see that the input here is the word embedding, so it should be the word embedding size. The input in all subsequent layers would be the size of the hidden dimension. And then for the softmax, or for the linear transformation before the softmax, we implement something where the output is the number of tags and the input is the hidden size. Okay, you'll notice this initializer Xavier uniform here. So what is this? Yeah, I'll skip to the initialization first. So the Xavier uniform is basically how we initialize parameters at the very beginning of training. And this is something I haven't covered before in the neural networks when I was talking about neural networks. But one very important thing of neural networks is their power comes from the fact that they're able to extract different features from words or context or something like this. And of course, the features need to be different. So if we, what would happen if we basically initialized all of the weights of a particular layer to be identical? Like, let's say we had a weight matrix. Let's say we had these weight matrices 1 and 2, and we initialized all the weights to be 0. What would happen then? Yeah.
But they all kind of have the same output, and then like the input back would be the same all the way, so they essentially always have the same weights.
Yes. Yeah, I'll repeat it because probably people on Zoom or maybe in the front can hear it. But basically, all of the outputs would be the same. And as a result of all of the outputs and all of the computations being the same, the gradients that flow back into them would be the same. So I think actually accurately, all of the rows, or maybe in this computation, all of the rows of the weight matrix, or all of the columns of the weight matrix would result in the same value. So you wouldn't have any difference of any of the outputs. They would always be the same. So to put it in a less mathematical term, basically you would be extracting one feature. It might be a very nice feature, but you would only be extracting one feature when in fact you want to be extracting lots of different features. You know, like this is a verb, this is a noun, this is a determiner. So in order to do this, we need to be making the initialization different for each of them. I had one question on Zoom. All the hidden layer sizes will be the same, is that right? For the implementation in classifier.py, that is the case. All the hidden layers will be the same size. There's no reason why you need to do it that way. You could change it so you had different size hidden layers. And in fact, it is common in some settings to have like a bottleneck layer where you have a bunch of big layers, and then you have a little layer in the middle, and then you have more big layers. And this is a good way to extract kind of very good features in the middle layer, because if the middle layer is not able to extract good features, then you're not able to learn in the face of this like very strict dimension reduction. So there's no, long story short, there's no restriction that the layers need to be the same size, but that's how it's implemented here. Okay, going back to parameter initialization. So neural nets must have weights that are not identical. So there's a bunch of different ways that we do this. They all have to do with randomly initializing the weights in some way. The one standard one is uniform initialization. So we just initialize all of the weights from -1 to 1. Sorry, minus 0.1 to 0.1, or some other span that we pick semi-arbitrarily. But the problem with this is, depending on the size of the net, the inputs to the downstream nodes may be like very large or very small. So like, for example, if we had a neural network with a hidden size of 256, and all of the inputs were in the scale of -1 to 1, the variance of the outputs would be about, maybe, I'm not sure if I'm getting the variance right, but like the basic idea is that the variance would be, if it was 256, you might expect things basically in the range of like -25.6 to 25.6. If you had 512 nodes, it would be between -51.2 and +51.2, et cetera, et cetera. And so you would, this basically causes the behavior of the net to be very different depending on the size you pick. So there are initialization methods like Glorat or Xavier initialization or initialization, which initialize based on the size of the matrix. And this is the example of Glorat initialization, where we have 6 divided by the input dimension and the plus the output dimension, and you take the square root of this. And basically the motivation for this is that this allows you to control the variance of the output to be relatively constant under some assumptions. So that's the version that that this app code used up here. There are other ways you can do this. There's actually a deep learning book that has a lot of description of this if you want to get the deep learning book, and you can actually measure the norm of the gradients that you get back into your inputs and set these so that the norm of the gradients is good. So there's other methods for this as well. Question on Zoom was, how does this scale in the case where you have a weight tensor with more than 2 dimensions? Yeah, that's a really good question. It depends on your like assumptions about the input. But if you make the same assumptions about the input for Glorat here, I believe, well, yeah, I guess it depends on whether you're assuming you're multiplying in 2 inputs to that, or you have 1 input and 2 outputs. If you're multiplying in 1 input, you should basically assume the 2 dimensions are like multiplied together, are d out. If you are assuming that you have 2 inputs and you multiply both of them in and get an output, I imagine, actually, I think I knew this at one point, but I don't remember exactly what you do. Does anyone here remember or no? I think you might, like multiply them together or add them together. That's a good question. Maybe we can leave it for Piazza later. Yeah, sorry, I don't have the answer for that immediately.
The question is
Yeah.
about varying dimensions or varying number of inputs.
So basically, if you have a tensor of size 3, what do you do with respect to this? And I think, sorry, tensor of dimension 3. So a 3-dimensional tensor. Yeah, yeah.
For Flora, like, do you initialize all of it choosing your CMU?
Oh, for Glorat. So basically, what this does. Oh, I'm sorry. This is very vague. So what this is this is the range of the uniform initialization. Sorry, I should have said that. So basically, instead of going from 0.1 to minus 0.1, this initializes the range with which you do uniform, and then you just do uniform sampling there.
So you still use the uniform distribution?
Yeah, it's just, it decides the range for you.
Why don't you use something like Gaussian?
Why don't you use something like Gaussian? That's a good question. You can use something like Gaussian, but I have tried it before myself, and Gaussian is worse, like empirically. I'm sure there's a reason for this, but I don't know it off the top of my head. I'm sure you could adjust the norm of the the variance of the Gaussian to have this like similar constraints here. I don't know if anybody else has a good DL theory about this. But... Okay, guess not. Yeah.
What's the significance of using dimension sizes in the denominator?
So basically, as I mentioned before, if the dimension size is like larger and you initialize with uniform initialization, the variance will get larger. And so you're dividing by the dimension size. So as the net gets larger, the initialization will get smaller. So it controls for this. The variance of any quantity will scale with a in square root with respect to the size of the quantity, basically. And the square root here is to control for that. I don't have the equations on hand here, but basically that's the motivation. Cool. Okay. And then the slide I skipped over here, basically, I talked about exactly how we initialize the parameters, but in addition to the parameters, we have a model that basically holds all the parameters. So the model is a collection of parameters. And the reason why we have this is that this will apply like our optimizer to all of the parameters in the model. So it will step through all the parameters in the model and make updates to all of them. Okay. So then if we go into the next step, this is definition of computation and calculating the results of that computation. We are going to be doing greedy or eager computation versus lazy computation. So we're going to step through the graph. If you'll remember from last time, we basically defined an expression, defined a graph for it, and we step through the graph, defining the computation, basically adding one node at a time. And then finally, we assign this node to like a name at the end, and this is the variable y. So this is what it looks like in app code. So we have this reset computation graph thing here. The reason why we're resetting the computation graph is very commonly, if you look back at the overall view of what a neural network code looks like, it's usually for each example, we create a graph doing the computation that we want, and then calculate the result of the computation. So we can basically reset the graph for every example. This is not what happens in PyTorch, for example. PyTorch has a more complicated thing where it's doing garbage collection of things that you're not using anymore. But that's more complicated to implement. So we're just garbage collecting everything before every example. And that's what this reset computation graph thing does. We then look up embeddings for each of the words. We sum them together. Then we go through each neural network layer. We calculate the matrix multiplication between the hidden layer and the weight matrix. We add the bias, and we take a tanh nonlinearity here. And then at the very end, we calculate the score by multiplying the resulting hidden state by the weight matrix for the softmax and add a bias here. So this is the entirety of the app code that we're going to be writing. You know, it implements our bag of words model here, but you know, basically more or less as is. And so then the next thing that we're going to be doing is defining in our backend code what a computation graph looks like. And so the computation graph, this is just like the way to get the computation graph. But the computation graph is also just a list of operations. And when we add something to the computation graph, we basically append the operation to the end of the computation graph. Pretty simple stuff. We also have operations, and operations must know how to calculate their value given the input, and also how to calculate their derivative given the following derivative. So basically, you know, that's what I wrote up here. And we want to store the gradient of the final function, like the loss function or something like this. And if you remember from last class, we're going to do that in a backward operation where we step backward through the graph. So we will calculate the derivative, we will calculate basically this derivative given the final loss, given what we know about the next derivative, the derivative for the following node. I'll show an example. So as an example operation, I'm going to talk about a ReLU, a rectified linear unit. And the rectified linear unit is an operation that takes in a tensor, and for every value in that tensor, it will return the value itself if it's greater than 0, and it will return 0 if the value is less than 0. The gradient basically is 1 if things are more than 0 and 0 if things are less than 0. So very simple operation. So what this looks like is we have a forward function that we define to calculate this value up here. And basically what we do is we take in the input data, and for every input datum where the value is less than 0, we set it to 0. Pretty simple. We define a tensor from this, and we also save some context, and this context is used later when we calculate the backward function here. After we've done that, for the backward function, we calculate in the context, and if the gradient is not none, so basically if we have a gradient for the following function, we basically set the gradient to be 1, like this gradient to be 1 if the value is more than 0, 0 if the value is less than 0, and then we multiply it by the following gradient. So just to clarify why we're doing this, remember what we want to calculate is we want to calculate the value of the final function given the previous function. And we're using the chain rule so that we multiply together the gradient of the following computation with the gradient of the current computation using the chain rule. So that's what we're doing here. We multiply this, which is the current computation, by the following computation. Any questions about this? Yes. It's just basically saving this so you can keep it around for later when you run the backward functions. So this store context is storing any information that you need from this forward pass so that you can calculate the backward pass. So for some things, you don't actually need some pieces of this context. Let me see if I can have a good example. So the gradient of the identity function is always, let me see if I can think of an example. So the gradient of a constant value is, the gradient of a constant value is always 0 independent of the following thing. So you wouldn't need to be retrieving the following thing or saving it. So that's the basic idea. There's lots of other examples of this, but I'm blanking on like a more, good example. I don't know if anybody else has one here, but that's the basic idea. You only keep around the stuff you need to calculate the gradients later. Yes.
P value is the following node. So array value feeds into P value.
So this is the tensor. This is the value of the following computation, or the resulting computation. Okay.
So on the previous slide, we saw that we multiply the gradient of the current node rectify the gradient of the following node with respect to, so this T value of the following node?
T value is the tensor representing the value of the tensor representing the input of the following node, basically. Yes. And the input of the following node is the output of this node. So,
Right.
yeah.
Okay, so that.
Yes.
Very last line is full forward.
Yeah, so full forward and forward are similar. Full forward would be going all the way from the beginning, like it's a recursive value going all the way from the beginning, I think. Yeah. Okay, so it's not calculating all the way from the beginning. Okay, sorry. I haven't looked at the code for super carefully for a year, so yeah, it's forward plus some bookkeeping stuff here.
Is there a reason why there's an if statement and the backward function?
Yeah, so if there is no gradient from the following node, then the gradient of this node is going to be null, basically. So if we're not getting it, like to give an example, I'll call this, yeah. If we have a computation graph that looks like this, where the right side is our loss function, this might still be useful. Like, let's say we have a loss function, but we also want to calculate something else at the same time. We want to monitor some sort of like auxiliary data. We would want to do something like this. But there's no need to calculate the gradient of this because we know the gradient is 0 because it's not connected to the loss function. So that's what the if statement is doing. Yes. Is there a reason why we have a separate thing here? Yes. Oh, in the. That's a good point. do you have a answer for that? So the question was basically why do we have t-relu and r-relu instead of t-relu.data? And the answer is you could do that too. We had another question on Zoom. Which was the same question we just answered. So yeah. Okay, great. So this is just one example of a ReLU. It's a relatively simple example because it takes in an input. It's also an element-wise operation. Element-wise operations are the most simple type of operation because they don't require, summing things across dimensions or multiplying things together. This is also a unary operation, so it's not multiplying. It's not like multiplying two matrices together. So we have some examples of more complicated operations to kind of bootstrap you into being able to implement them in the code, so you can look at those too. Okay, so for backpropagation, if we're training, we'll want to be doing this. And backpropagation, basically, we start at the end. And assuming this is our loss function, assuming this is the thing that we want to be calculating derivatives with respect to. We also assume it's a scalar value, so we can only have like a single loss function. We can't have like a vector of loss functions or something like this. So assuming this, the derivative the derivative of the last node will basically be the derivative of L with respect to L. And that's always 1. So we set this to 1. And then after we've set this to 1, we recursively run the backward function, which can calculate the value of all of these based on the following values. So this is what the overall backward looks like. And so basically we just step backward through the whole graph. We have the operation, and yeah, and so this alpha is setting the first gradient to 1. And then we step back from the operation that we're interested in and run the backward function over all of them. So the reason why we're like starting at the index here is just if we had a graph that looked like this. Actually, it'd be B0 index, but if we had a graph that looks like this, we just wouldn't have to do 5 and 4 if we only cared about the gradients from 3. So that's the whole backward code, basically the whole backward algorithm. And now we get into things that are a little bit more tricky. So parameter update. The way we update parameters is basically we want to move the parameters in a direction that decreases the loss function that we care about. There's many different update rules that we could be using. The simplest one is a simple SGD where we update with only gradients. Then we have other things like momentum, edigrad, and atom. And atom is the most commonly used one now. So atom is basically a combination of momentum and adaptive and edigrad. So I'm going to explain each of them in turn. So what standard SGD does is it calculates the gradient of the loss function with respect to certain parameters. So we'll call this GT. And yeah, that's the gradient of the loss with respect to the parameters we're interested in. And we then update by multiplying this gradient by learning rate and subtracting it here. So every single time we'll take a step in the direction of the gradient. This is with respect to a single parameter, theta. So like this is the update rule for a single parameter, but basically all of the optimizers that we use standard in neural networks are first order optimizers. So they basically, or they're optimizers, sorry, first order is not the right way to say that. They're basically optimizers that optimize the individual parameters on their own and don't consider interactions or covariance between them. So the way the SGD update rule looks is we have the SGD trainer. We have a learning rate in here. And we have an update over the model parameters. And then we have this update sparse and update dense. And the update sparse and update dense are different. Basically, the way update dense works is a very simple thing. It's updating just all of the parameters according to this function. So this is not super complicated. What update sparse does is it has a list of gradients it has a list of gradients that have a list of parameters that have non-zero gradients. So what it does is it steps through each of these gradients that have non-zero parameters, each of the parameters that have non-zero gradients, and updates them according to the update rule. And so why would we want to do this? Let's take an example. The most obvious example here is of word embeddings. And let's say we have a word embedding, I like it, or a sentence, I like it. And we have a vocabulary size of 60,000 or something like this. So what we could do is we could take our huge 60,000 embedding matrix and we could update the whole thing, or we could just take the 3 rows that correspond to I and like and it and update these. And especially if we have a kind of complicated update rule like atom, the update is a non-trivial cost. If we have like a small batch size complicated update rule like atom and we're using a CPU, any of those things above. And if you want to do something like this, you know, doing a sparse update over just the things we want to update is a more effective way of doing things. This would also be really important if you're like training on a cell phone or something like that. So if you want to deploy something on a mobile device, then you know, of course, you're not going to have a big, powerful GPU that can do all these matrix operations. So now that standard SGD are things okay here? Any questions? Okay. So then the next thing is SGD with momentum. And basically, what SGD with momentum does is it remembers gradients from the previous time steps. So instead of updating just with the gradient, we have the momentum, and the momentum is based on the previous momentum with a momentum conservation parameter, which tells us how much momentum we want to be continuing to keep. And then we add the gradient into this. So if we set this to like 0.9, what this means is every time our momentum will be decreased by 10%, and we add in the gradient here. So approximately you know, our gradient would be similar to the gradient from the past 10 steps or so. Just, it's not exactly the same, but you might get the idea from that. If we set this momentum conservation parameter to 0.99, it would be approximately like having the gradient for the past 100 steps. And then when we do the update, we do the update based on the momentum as opposed to based on the current gradient. The intuition about why we would want to do this is we'd want to prevent instability resulting from sudden changes in the gradients. Another thing here is edigrad. So edigrad is basically adaptively reducing the learning rate based on accumulated variance of the gradients. And what I mean by this is basically we calculate the variance of the gradient by multiplying GT together with GT. That gives us a variance. And this is the squared current gradient. And then we divide how much we update based on this variance. So to give a little bit of intuition about why we would want to do this is frequently updated parameters should be updated less. So like to give the example of word embeddings, let's say we have a very frequent word like the. We've probably seen it, you know, 5,000 times or, you know, 5 million times throughout training. We're pretty sure of what its word embedding is going to look like. And so we don't want to be updating it wildly based on a single example. However, if we have a different word embedding like explicit or exquisite, that would not be very common, but it might be very useful. So we would want to make a big, bold update of those parameters. And so what we do basically is we look at all of the variance of the parameters that we've seen so far, and we divide by that. And so the parameters that have seen lots of updates or big updates in the past basically won't be updated as large. Okay. So one problem with this edigrad is that the learning rate continuously decreases because we're always adding in the variance. So it just gets smaller and smaller as training goes on. So there's other methods like edidelta and RMSprop that fix this issue. But that brings us to Atom, which is optimizer you'll be using a lot of the time. And it considers the rolling average of the gradient and the momentum. So basically this is like our momentum term. So basically we're adding in 1 minus beta 1 to GT and the momentum that we have from the previous time. So this beta 1 is our gradient momentum conservation parameter. And then we also have a rolling average of the variance. And this beta 2 is like our variance momentum conservation parameter. We also correct the bias. We correct the bias of having very small, of having very small momentum terms in the beginning of training like this. And then our final update term looks like this. So it looks very similar to the edigrad update as well. So long story short, Atom combines those two ideas together. It has a momentum term to prevent sudden large changes, and it also scales the variance. Okay, any questions about this? This is something that you could implement during the assignment if you want. Okay. So finally, I'd like to get into some training tricks. So these are some things that are very useful to know. One thing that you definitely need to know about and should have implemented in this assignment is shuffling the training data. The reason why is because stochastic gradient methods, so basically methods that do updates on a small part of the training data every time, they can be biased towards more recent gradients. So like, let's say we have a data set that was created in a very biased way, where all of the positive examples are after all of the negative examples. And then we do one pass through the data. Basically what that will mean is at the end of training, we will have seen all of the positive examples many, many times in a row before seeing any negative examples. So we'll have something that's very biased towards training on the positive examples. So to train correctly, we should randomly shuffle the order at each time step, or even randomly sample from the data that we have at each time step. Another issue that you will face is overfitting. And overfitting is basically where you learn a model that's very good on the training set, but not very good at generalizing to the test set. Especially for bigger neural networks, they have tons of parameters, and we want to prevent them from, basically memorizing the training data without generalizing well to new data. And basically the way we solve this is by some sort of regularization. And what I mean by regularization is we don't let the neural network just optimize the training loss forever so that the training loss gets down to 0. We have some way of preventing it from getting that far in training. And the most common variety of essentially regularization on our model is to do early stopping, where we stop training before the model fits the data completely. And the most standard way to do this is to monitor performance on a held out development data and stop training when it starts to get worse. So basically we train until we have some data that's not in our training set, and then stop when the accuracy gets worse there. Another thing is learning rate decay. So we can gradually reduce the learning rate as training continues. And basically what this does is this gets the model to stop learning before it overfits. It also stabilizes training somewhat, because if you have a large learning rate, you might learn very quickly, but it's a bit unstable. If you have a small learning rate, it's more stable. Another thing you can do is reduce the learning rate when the dev performance plateaus. So when you hit the point where you would be stopping training, instead of stopping training, you reduce the learning rate and then continue training from the place where you would have stopped. If you are going to do something like this, though, you should be familiar with the concept of patience, where basically learning can be unstable, unlike convex optimization problems, where basically you can guarantee that your loss will get better every time. Neural networks are a complex non-convex optimization problem, so your loss might go down, 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 up a little bit, down, down, up a little, down. So the idea of patience is basically even if your dev performance gets worse, you keep training for a little while until you're really ready to give up and you're sure that it's not going to get any better. So you wait n times. Okay. Any questions about this? Yeah. Oh, very good question. No, you can use it for anything. Actually, I think I have slightly misordered slides, so I'll get to that in like one slide. I'm having this great duplicate question on Zoom in class. So I had the same question on learning rate decay. So I'll talk about that in one slide. Okay, so next question, next one is which optimizer should we use? Atom is usually fast to converge and stable, so I would recommend it as your default. However, in both my experience and some reports, SGD has been found to do very well in terms of generalization. Sometimes if you want the absolute best performance, it might be a better idea to use SGD, like simple SGD. I have also seen people training with Atom first because it's faster and then using SGD at the end of training. That starts to become a dark art. So I don't know if you really want to like get that far, but that's something you can consider. Another thing is you should definitely use learning rate decay. I've found it to be good all the time, including with things like Atom. So you can use learning rate decay on the development set. Also, one thing that I forgot to add to the slides here is the standard training method for transformers, which we'll be talking about in a few classes, but I think a lot of people know about, actually has this very strange learning rate schedule that goes like this. So it basically warms up and then cools down at the end. So that's kind of like the standard method for training transformers, and it's actually pretty important for getting them to converge. Another thing that you should be doing basically all the time is something called dropout. And the way dropout works is neural networks, because neural networks are prone to overfitting, what dropout does is it randomly zeroes out nodes in the hidden layer with probability P at training time only. So we take the hidden layer and we take some of the nodes in the hidden layer and we zero them out like this at training time. And then at test time, we don't do this. And basically what this is doing is it's making training harder so that you do better at test time. To give an example, it's like jogging with a weight vest on, so you're really good at soccer later, because you do it harder until you actually need to perform. There's a number of different like interpretations of this as well, but you can think of practically what the problem it solves also is it makes it much harder to memorize individual data points. Because one way you could memorize individual data points is you could set a node that basically is active for each individual data point and then use that to classify. But dropout prevents that because that node might get zeroed out. So you need to spread the information all the way across the vector. There's also a view of it from like ensembling multiple models together, but we can talk about that later. One detail when you implement this is you need to scale the size of the outputs. So if maybe I can just talk about inverted dropout. So basically, what is happening here is if we drop out half of the nodes at training time, the size or the total like norm of the vector is going to be half the size it will be at test time. So you just multiply the vector by 1 divided by 1 minus p. So if p is 0.5, you would be multiplying by 2 at training time. which would make the scale equal to what it would be at test time. There's also other alternatives like drop connect, which zero out weights in the neural network. These are useful if you have like a model where you can't modify the internal representations, but you can modify the weights. So there's also other alternatives. Okay, so the final thing, this is kind of a distillation of lots of neural network knowledge that you need to know for training neural nets for NLP. So this is the last one. This is very, very important. The idea is operation batching. And the reason why we want to do this is it's actually twofold. The one is for efficiency reasons, one is for training stability reasons. And basically, the reason why we do it for efficiency reasons is on modern hardware, doing many operations at a time, many identical operations at a time is much faster than doing operations individually. So to give an example on a GPU can add numbers, add like 256 numbers at the same speed it can add one number because it has 256 threads or 512 threads. So if you can group together 256 additions, it will be just as fast as if you did only one. It's also the case on CPU. I don't know if people realize this, but CPUs can do, anywhere like 16 to 32 additions all at the same time. So modern CPUs also have this ability. So mini batching basically tries to convert any operations in our neural network from smaller ones to bigger ones. And just to give an example here, let's say we have a whole bunch of hidden layer calculations where we're multiplying W and adding B. And so what we do is instead of multiplying like 3 input vectors together separately, we concatenate all of them together and then we do one bigger matrix multiply because this is faster, essentially. We then take this vector B, we do an operation called broadcasting, which basically pseudo duplicates it along a dimension. So it's not actually duplicated in memory, but it's duplicated for the purpose of running the operation. And that's supported in NumPy, CuPy, any toolkit that you're interested in. So basically what we do is we group together similar operations, loss calculations for a single word, execute them all together. In the case of a feed-forward language model or something like this, each word prediction in a sentence can be batched together because they're all the same shape. They all use 2 previous words to predict the next word, for example. For recurrent neural networks or any other thing where we are processing like variably linked sentences, it would be more complicated. Most toolkits will require you to add an extra dimension representing the batch size. So to give an example here, we took a whole bunch of vectors, which are of dimension 1, and we turn it into a matrix, which is of dimension 2, and one of the dimensions represents the batch size. Some toolkits have explicit tools that help with batching. So, for example, PyTorch, you can take a whole bunch of sentences and put them together in like a padded sequence that would allow you to do this without doing some of the hard work yourself. One other thing that I don't have on the slides, but it's another very important feature of batching together similar operations, is one of the big issues with stochastic gradient methods, with methods that basically calculate gradients on a single example, is calculating gradients on a single example is much more efficient than calculating them across, the entire corpus, for example, because a single example is just one example. The entire corpus might have 1 million examples, and calculating gradients for 1 million examples is slow. However, for a single example, the gradients will be very noisy. Just to give one example, you might only have positive labels or negative labels. Mini batches, if you have a mini batch of, 32 sentences or 64 sentences, that's going to be much more stable than the gradients on a single example. It will be still less stable than the gradients on the full corpus. So there's kind of a trade-off there with respect to speed and stability. Another thing that you should know is kind of the noise induced by stochastic gradient methods helps you get out of local optima at the very beginning of training. So for neural networks, it's not necessarily the case that training on the full batch of data, like the entire corpus, would give you better results either. So basically, the larger batches will give you more stable training. It's a good idea to do. It's a good idea to do larger batches sometimes when you can. A couple other things to note. So let's say you have a GPU and the GPU has like 12 gigabytes of memory. I hear a lot of people saying, I would like to train with a batch size of 64 because it would make my training more stable, but I can't because I can't fit it on my GPU. That's actually not the case. I like to separate like the computation batch size and the learning batch size. So let's say our computation batch size is 32 because that's the number of sentences we can fit on the GPU. So the normal way we would do this is we would calculate the gradients for 32 sentences and then do an update. And then do another update down here. But we don't actually have to do an update and clear out the gradients every time. So we could just skip this update and keep on accumulating gradients, and then we can train with a batch size of 64. And in fact, many people do this, train on 8 GPUs where each GPU does 32 sentences, and then you would be able to do 32 times 8, which is how many? 256. So this is an important thing to know if you want to stabilize training for large models. This is numerically equivalent to having a batch size of 64 because the gradients, we assume that each example is independent. And so the gradients of, like, let's say we have loss I equals 164. The sum of the losses will be 64 here. And so if you have that in 2 batches, the sum is still the sum, right? So yeah, it's numerically equivalent. Any other questions? Okay, that is all. The assignment is the assignment here, which now I think everybody should get started on, is we've left off details of the neural network toolkit here, and you will have to go in and implement them. And this will demonstrate and deepen understanding here. What's that? Oh yeah, you'll submit it on Canvas. There's one thing that we're going to update, which is we have a assignment verifier, but we're going to change it into an assignment zip file creator script. So basically you'll run this assignment zip file creator script, which will verify the format of your assignment and create a zip file, then you'll submit it through Canvas. And that Canvas will be open very soon. Great. Okay, thanks everyone.